Hello, and welcome to this talk on automated workflows for system modeling and controller design. I'm Subha Thomas, and with me is my colleague Sergio Vargas. Sergio works on the system modeler side of things, and I work on the control system side. And today we will be presenting some of the results of our collaborative efforts. One of the things that we've been working on since version 12.3 is to smooth out the bumps in the workflow as we go from creating a model in system modeler to its analysis and controller design in the Wolfram language, and then back to system modeler for further simulation and analysis. In the first part of the talk, I will illustrate these improved workflows using some simple self-contained examples. And in the second part, Sergio will illustrate them using system modeler examples. So we have uploaded the notebook to Pathable, so you can download this notebook from there and follow along that way too. Okay, so let's start with a regulating controller. Here I have a very simple system with one state and one input. The eigenvalue of this system is 1, so it is unstable. So if I start the system from any non-zero initial value or any input, the system will blow up and it will end up at infinity. What a regulating controller does is apply a control law of the form U is equal to minus kappa X plus U bar. This is the state feedback part, and this is an exogenous reference input. So with this input, if you plug it back into these equations, we get a modified system where the eigenvalue is 1 minus kappa. So using this value of kappa, we can modify the eigenvalue of the system and thus tailor the response of the modified system. This is the implementation of that controller. Here I'm using state feedback gains to compute that controller. I'm giving the system I want to regulate and the desired closed loop pole, and state feedback gains says that with a gain of k, when k is 1, the closed loop pole is -3. And then I can put that system and the controller together in a state feedback configuration and get the closed loop system. And now when I plot the output response, the system is stabilized and it reaches a finite value. But what that did was regulate the system, but it didn't, just with this, we cannot track. I gave an input of 1 and the system's stabilized at some other stable value. To track, we need a tracking controller. So I have the same system as before. And in this tracking controller, we have the state feedback component as before, but then we also have an additional component that depends on the integral of the error. Now with this, we get these as the modified equations. Here, the first equation here defines what the error is. The error is the reference value minus the actual value of X. This is what I'm trying to track. And the second equation is obtained by substituting this value of U into those equations. So the kappa E remains the same and the coefficient of X is changed as 1 minus kappa. So if we stabilize this matrix or get its eigenvalues to be stable, in steady state, E will go to 0 and X prime is 0. X will reach some finite value such that the error is 0. And this is the implementation of that controller. Again, I'm using state feedback gains to compute this controller. So here the specifications are a little more detailed. Earlier, when the regulator problem, I just gave the system and that it assumed as the input model and none of the outputs were tracked. When we want to track, we explicitly say what is the output that we want to track. The system has just one output and that's the output I'm tracking. And these are the closed loop poles that I desire for the modified system. Now over here, putting this system together is more involved than before. I do it in 3 steps. First, I do a state feedback connection, which reduces this system with the state feedback component. Then I put it in series with the error feedback component. And once I've reduced the whole thing, I do that system in feedback to get the complete closed loop system. And now when I compute the output response for general reference value gamma, you see that the transients I have are the closed loop poles I specified. And once they die out, the system reaches the desired reference value. So what we have seen in these two examples are two very simple cases of regulation and tracking. Okay, in general, the system could have other inputs as well. They are disturbances. They can be stochastic disturbances. They could be deterministic ones. The other thing is over here, I assume state feedback. Okay, sometimes we do not have all the states available for feedback. We need to use output feedback. And some of the outputs are tracked, some are not. Sometimes we could have a continuous time system that needs to be put together with a discrete time controller, which is a sampled data configuration. And so we could have all these different kinds of layouts. Okay, so once we have these different kinds of layouts, then getting the closed loop system, computing what's the controller model, computing various other aspects of the system, it's not difficult, but it's not trivial either. And that is the motivation for this effort, so that all these routine computations that are part of this design are automated and readily available as properties. So let's look at the same design in the new workflow. So I have the same system as before, and if I want the closed loop system, I just simply ask for the closed loop system, and I get it directly as a property, and then I simulate it as before. And same thing for the tracking. I have the system as before. And when I want the closed loop system, I ask for it directly as a property. As you saw in the previous slide, getting this closed loop system was more involved than in the regulator case. But from a user perspective, that doesn't matter because you get it directly as a property, and then you can go right ahead and simulate it and see that that is in fact tracks the reference as was expected. So this is an overview of the new workflow. We can start with a model, either from system modeler, or you can specify the model manually using one of these functions, or these models can be obtained using some other techniques. And then all these functions accept these models. And the way you specify them is in a very uniform way. And once you specify the model and the controller parameters, the common properties are obtained directly by specifying those property values, or you can obtain a controller data object that then we can use for further analysis or simulation or deployment or the other downstream tasks. Okay, so let's look at that controller data object. So earlier we obtained this closed loop system. If you want the feedback gains, we can ask for the feedback gains. The disadvantage with this approach is that if you each time we call this, the computations are starting again from scratch. And so that's why we have this data object. It's nothing fancy about this. It's just like the other data objects in the Wolfram language. So once you have the data object, then you can obviate some of the computations. Like if you're now computing the closed loop system, yes, it based on that, it puts together the closed loop system. But then if you want the feedback gains, there's no additional computation. It already knows what the feedback gains are, and it will return those feedback gains there. Then we can ask for a list of properties. Yeah, one thing I want to point out is that in some cases, some properties have additional specifications, and they are given as a second argument, in the second argument as an association. And we can give a list of properties, some of which have additional specifications and some which don't. We can get all the properties as an association and also as a data set, just the standard fare. Another workflow could be that somebody else did the controller design, or you did the controller design and you want to give it to somebody else. So you can just give them this data object. And then from this data object, we can query what are the properties, we can get their values, and then from here, we can go on to do the further analysis. So this is what happens when we interact with system modeler. What we pass on is this data object, and it uses that to put together the closed loop system and simulate it and do the other tasks. Okay, so let's put this together and look at a small example. So here I have a coupled pendulum system. The force on this second mass I'm using as my input force, and I plan to use that force to control the position of this first mass. And this force on this first mass, I take it as some disturbance that is acting on the system. Now this is a model of the system, and this is the disturbance force that I'm going to apply on the first mass. So I compute the response of the system, and that's the first input is that disturbance. I don't apply any force to the second mass. And as expected, you see that pendulum begin to oscillate. I have not incorporated any friction in the model, so it just keeps on oscillating. So to track it, now I'm going to give the input specification. So this is not as is not just having one feedback input as before. So I have this input model, which is my pendulum system. And I have to say which is my feedback input. The first one is a disturbance. So I say that the second input is my feedback input. Of the three outputs, the one I want to track is the angle of the first mass. And here I'm by default, tracking happens for a constant signal. Here I just want to illustrate how we would track other signals. You can give what its governing equations are. So in this case, I'm tracking a sinusoid. Okay, that is the system specification. And the control law I'm using here, the control technique I'm using here is actually an optimization technique, which says that I want to minimize these quantities. Okay, so minimizing these quantities will actually stabilize and drive the system to its desired objective. And what I have to specify in those cases are the weights to these various terms. So I penalize the error the most, and then I also penalize the two angles. And that's a design choice. So once I have the system specification and the weights, I get the controller data object. And from that, once I have that directly, I can compute what the closed loop system is. Now, if you look at the closed loop system, it has two inputs, the disturbance and the reference. So I compute the response of the system to that disturbance and that reference. And okay, and the states are, the first one is the angular velocity, the angle, and so on. So the first one is the angle of the first mass, and we compare it to the desired sinusoid that we have. So now it's oscillating at a very different frequency from its natural oscillations. Then I can look at what the controller model itself was. So if you look at the controller model, okay, the controller model has the reference and the states as input, and that's using that to compute the force that needs to be applied there. And so I give those as the inputs to the controller model. And then I can see what the controller effort is. So in this example, I assumed that I could measure all the states, but over here, I'm assuming that I cannot measure all the states. I can only measure two of the outputs, that is the angular velocities of the two masses. So for that, I had to design an estimator. So I look at what the closed loop poles of the tracker are. I place the estimator poles a little more to the left. I compute a set of estimator gains, and then I use the function estimator regulator to put that tracker and regulator together in this configuration. And that also gives me a data object. So here I'm saying what are the outputs I'm measuring. So one of the ways we can check whether we are right so far is to look at the closed loop poles of this complete system. And that should be the poles of the tracker and the estimator together. And that's what I'm verifying that it is true. Then in one shot, I get what the closed loop system is. It can be a little involved to actually do it by hand, but now with this property, we just get it directly. I look at its state response. And again, the first one is my angle, which I then compare with the reference. And yeah, after some time, it begins to track. I look at what the control model is now. Yeah, and the control model now has three inputs. One is the reference, the other is the two measurements. It looks at what the reference value is, where the system actually is, and then the controller computes the actual force that needs to be applied to the second mass. And then I can plot the controller effort. Now, then we can relax one more assumption and say that, okay, I have these sensors, maybe these sensors are noisy. And so now I get the closed loop system assuming that the sensors are noisy. And I generate a set of noisy signals and apply that to my closed loop system. So now I have two additional inputs. This is just like before, but now I have two additional inputs coming into the system, which are the noisy inputs. I apply that to the system. I see its response. Again, the first one is the angle theta, which I don't have it here, but as you can see, it's a sinusoid. going from oscillating between 10 degrees, and then I compute what the controller effort is, again with the noise. So far I've shown you the workflows using just in the Wolfram language. Now that concludes my part of the talk, and now I'll pass it on to Sergio. He will show you the same workflow from a system modeler viewpoint.
Hello. Yes. So I have this split up setup in order for me to show you both what is happening in Mathematica and System Modeler. Let me first mention a couple of things about System Modeler. So this is kind of what you get when you open System Modeler, and it's a graphical environment where you can just plug and connect things, and you get like a more physical modeling approach to control systems. And from the point of view of Mathematica, the way these models that you have in System Modeler manifest is in the object system model. So for instance, this is a specific model in our libraries, and then I can right click here on this guy and say open in new system model center, and I get the diagram of the model that we are working with. So in this case, as you see, we have very basic components, a DC motor, and then some inertia that rotates. And from then on, I can use this object in Mathematica, and then I can pass it to system model functions. So I can do, for instance, pass it to system model linearize. And then I get a linear state space model like the ones that Suba were showing before. I can plot things from my model, variables or parameters. And thanks to the work that we have been doing, we can now pass directly system model objects to the control functions, like the ones that Suba was talking about, in this case, PID tune. And then I can get a controller directly generated towards this model in System Modeler. But let's look for more applied and more interesting examples in System Modeler. So for instance, let me start with a more involved system that has, again, a DC motor. So let me just open this in System Modeler Center. Great. So as you can see, this is a bigger model. We have a DC motor, but now we are also passing our rotational energy to a translational system, which consists in this case of a cart under a mass, and there's a mass that acts like a pendulum. And the idea of this system is that we want to keep the pendulum inverted all the time. So we want to keep it in vertical position, despite the fact that we're gonna affect it with disturbance forces. So I go back to Mathematica, and we follow the workflow that Suba was showing up. So basically, I can linearize my model. So I pass it to system model linearize, and I get a state space model. And then I generate a controller based on this linear model. In this particular case, I specify that the feedback input should be the voltage that enters in the DC motor. And then I can just use connect system model controller and pass the information in the controller data that we generated from the control and the original model. And with that, I immediately get a full system model that I can also visualize in Model Center, which shows here my original system with the state feedback and a comparator and all the stuff that we desired. And now we can perturb the system and see how the control system behaves. So in this case, for instance, I'm gonna give a couple of bumps to the pendulum to see how it behaves. And I can simulate and plot. And what I see is that the angle of my inverted pendulum only changes by 12 degrees or so. And I can also see what kind of voltage was needed in order to keep my pendulum in the inverted position. So this is kind of the workflow that we wanted to simplify and show. Another kind of situation that we can, another kind of field in which we are also interested is in chemical engineering. So for instance, for a continuous stirred tank reactor, we have also models in System Modeler, and I follow exactly the same workflow. I linearize it, I generate a controller, and I connect the controller to my original model. And as you'll see, this is a little bit, this model is a little bit more convoluted. In this case, it also has an estimator. And also we have inputs for noise in our system. And again, I can just perturb the system and see how it behaves. In this case, I'm just going to give a concentration for one of the reactants to be off from the equilibrium point. And eventually the system comes back to the original equilibrium position, because again, this is a type of regulator controller. But the newest thing that we worked was tracking controllers, right? So let's show that for system modeler as well. In this particular case, one of the typical examples in control systems is a ball and a beam system. So we place a ball on top of a beam, and then we control the rotation of the beam with some torque. And the idea is to balance the ball or make the ball move in a specific trajectory. So again, we linearize the model. We generate a controller, but in this case, I specify that I want to control the position of the ball on top of the beam. Then I connect it to my original model. And as Suba showed us, there you go. As Suba showed, this requires now the introduction of an integration block that is going to help us make the position of the ball to follow a specific reference. So now I can just provide reference to this tracked controller, and then my system is going to behave as desired. So in this case, for instance, I'm going to make the ball move a little bit to the right and then move a little bit to the left without it falling out of the beam. And then, so yeah, so I provide this kind of reference, and as you see, the final behavior of my model is very similar. And I can also see the kind of torque that I had to implement in order to keep the ball moving in that position. But we can make this a little bit more interesting. So system model provides immediate access to animations. So I can make this a little bit more interesting, make 6 copies of the system and provide them with different tracking references. So in this particular case, I'm just gonna give a little bit of a delay for each of the ball and beam systems. And what we're gonna see is that the system indeed behaves as I command it to. It's just gonna take a bit in order for the animation to load. While that runs, I can look into next example, maybe, perhaps. So we have also implemented small examples like a simple model for a submarine. And we can, in the particular case, we can track, for instance, the depth of the submarine, so we can make the submarine submerge with a specific base. Again, we follow the same procedure. We take the model, we linearize it, we specify which inputs we want to track, and then we connect it to the original model. In a second, I think we're gonna get the animation for the first one. Again, as you can see, we can provide specific, there you go. So now we have 6 ball and beam systems. I can provide some indication of how the balls rotate, and I can run the animation. And yep, so as you see, the beams are rotating as we specified them. So we're providing a specific amounts of torque on each one of them in order for the balls to follow specific trajectories. And as you see, they are a little bit, one is slightly delayed from the other, as I requested from the reference. Good. Same story for the case of the submarine. I provide a reference, and then the submarine moves accordingly. I think we can probably also run this animation. This might take a little bit short, a little bit of a shorter time. right. Another aspect in which we worked deeply was also improving discrete controllers. So those are now using the latest in discrete modeling in Modelica, which is the synchronous library. I can show that in a bit. Right. So here we have our submarine. And if I remember correctly, if we can align it a little bit, yes. So if I remember correctly, I think we provided a reference in such a way that just the tip stays out. Right. Yep. Another aspect in which we have looked into, and we have a blog coming up, is about stabilization of cameras. So we have a model for camera stabilization, which we can see here in Model Center. So we have a couple of masses, springs between them, and a mass on the top that represents our camera. And the idea is that despite of the forces that are acting over these two kind of bodies, which we could represent like a car, we want the camera to be stable at a fixed level. Again, we specify, we linearize the model, we generate a controller, and we connect the whole model. And the model that we obtain has, in this case, because I requested, is a discrete model. So we have a sampling period of 0.05 seconds. We perturb the system, and we can also generate an animation. So let me just jump directly to animation to see if we get it running with enough time. Right. And yeah, just to conclude while the animation runs, basically what we have shown is that there is an enormous space here in order to an enormous, a magnificent environment for us to provide amazing tracking controllers. And we have shown that they can work nicely over system model objects. And we are slowly improving the workflows that we have provided in order to provide a better integration between system modeler and Mathematica. So this is the animation, just to conclude. So the idea is that the two masses at the bottom are oscillating a lot, while the one at the top is not moving as much. There again, yep. And we can also add some nice cat shapes here so that this looks nicer. Yeah, and I guess that's all I had to say.
All right, thanks, Jan. Thanks, Mahar. While we are waiting for any questions, what I would like to reiterate is what you see from this talk is that we have really streamlined the controller design and integration with system modeler. As Sergio and Sergio especially were showing all those examples, you see that same workflow being reiterated over and over again. So all the complexities of the various controllers are hidden behind those automated functions. So hopefully this streamlines how you design controllers and put it back in system modeler. Okay, there's a question from Joseph. Says, does system modeler have any capability for interfacing with physical objects?
Right, yes, we have some libraries to interact with sensors. I think we have one specifically for OPC. And we have also pursued all kinds of co-simulation systems. Yeah, but we have support for this kind of stuff.
And Sergio, should we also mention model plug? Right,
yes, indeed. Right, so you can explore all these libraries in our website. We have in system model, we have a good set of libraries that support sensor input.
Okay, I think the chat is closed. I think our time is up. Thank you, everyone.
Thank you.
Thank you. Thank you. Bye-bye.